Investigation 1, determining the probability of an event. This is found on page 53 in your textbook or on your online textbook. Thanks for following along. Probability is the measure of how likely a given event or outcome will occur. The probability of an event can be written as a fraction or a decimal, ranging from 0 to 1, or as a percentage from 0% to 100%. A lot of times when we talk about this range of probability, we actually like to equate these mathematical numbers or percentages to just our regular language. For example, if you look at the scale right here below where it says range of probability, something that is impossible to happen has a likelihood of happening at a rate of 0%. 0% chance of rain, impossible, it's not going to rain. Now, maybe in the weather forecast that's not always true, but if something is 0% chance or impossible to chance, it has a range of probability of 0%. On the opposite end, if something is certain, 100%, this is going to happen, it's given that 100% designation. You would obviously find that halfway, if something is 50% chance, it's as likely to happen as it is not to happen. It's a 50-50 chance. And then you have the scale from 50 to 100 is something more likely to happen, or 0 to 50 unlikely to happen. So we're going to be familiar with using those words as ways to describe those percentages. For example, in this numbers 1, 2, 3, and 4, let's use those words: impossible, unlikely, likely is not, likely or certain, to describe the probability of these events. Number 1, Jake rolls a number less than 7 on a number cube. Well, if I have a die or dice in front of me, I know that there's a 1, 2, 3, 4, 5, and 6 on that number cube. And this says if he rolls a number less than 7. Well, 1, 2, 3, 4, 5, 6 are all less than 7. That means it's 100% certain that he will get a 1, 2, 3, 4, 5, 6, or 7. So I've applied that probability mathematically to the situation of the event here. In number 2, February will have 30 days. Well, February has 28 days. On a leap year, it's got 29 days. Because of how our Earth rotates, 365 days a year is actually one day too long overall, or too short overall. So every fourth year you have to have an extra day built in, because there's actually more than what would be that 24-hour span in each year. So we build in that extra day to make up for that total time for that orbit. February will never have 30 days, therefore it is impossible. Number 3, a tossed coin will land on tails. You're going to see this in Mr. Shane's exploration experiment in just a minute, but a coin has a head side and a tail side, so there's a 50-50 chance. It's as likely as not to happen. And then Shayla correctly guesses a number between 1 and 100. Well, the probability of that happening is 1 out of 100. If you had to put that as a percentage, 1 out of 100 is actually 1%, so you're way down here as unlikely. Not quite impossible, but very unlikely that if I picked a number, that you would get a chance to guess that out of 100. Maybe if you knew Mr. Shane and you would be able to guess his favorite number, then you would probably have a higher likelihood of guessing that. But in this case, 1 out of 100 is a very low chance, so therefore our probability is described as unlikely. In our lesson today, we're going to apply both this way in which we would apply a number scenario to a probability, and also the actual experimental calculation of probability. Experimental probability is the measure of how likely it is a given event will occur based on repeated trials. So basically, you're not just saying, well, how likely is this to happen one time? You're going to roll that dice each and every time, or multiple times, multiple trials, to figure out what those numbers would actually be. In this case, the number of times an event occurs and the number of trials are calculated. So if you have a specific event that you're looking for versus the number of times that you are trying something, that would give you your fraction here. You'd fill in the numerator and denominator, and that's actually able to give you what would be a fraction, can be changed to a decimal, and or to a percentage. 8, the exploration portion of investigation 1 asks us to do an experiment to figure out experimental probability. Now there's one that's listed in your textbook, but we're going to do one differently together in class today that has you a little bit more involved. Now before we start, just remember that experimental probability is defined by finding the probability of an event, the likelihood of something happening, based on the total number of trials. So in our denominator, when we're calculating this, you keep track of the total times that you're testing something, and then you keep track of the specific category, the number of times an event occurs. Now, whenever you're looking at experimental probability, you have to look at what are the different types of events or outcomes that could possibly happen, and then you create this tally sheet or frequency chart that's listed right in your textbook. We're going to do that together as I go through picking sticks. I got my fancy dancy teacher coffee mug here, and then I've got all your names on these sticks. I'm going to go through and choose one of those sticks. So that is the outcome that we're looking for, and the two different possibilities is obviously if it's a lady or gentleman that finds their name on that stick. We'll keep track of those. I won't do all of them, so you won't all hear your name called, but then we'll tally those and calculate the frequency. From that frequency, we can figure out experimental probability by putting those into a fraction. And lastly, you gotta be able to turn those fractions into a decimal and turn those decimals into a percentage to work with probability in its full scope and sequence. Let's get started. I won't look just so there's no bias. Chantel, put that one for the ladies. Not looking. Quinte, bringing the score even. Martavius. Makaya. Now you got to remember, Allison. I don't know what the actual ratio is between boys and girls in our class, so this is completely randomized. Genesis. Brianna, 5-2. Nadia. Brandon. So that's 5, 6, 7, 8, 9. Let's do one more. Malachi. All right, I only did 10 total trials. The number of trials was 10, and the tally and or frequency of each of those categories is right here. If we would keep going, we'd find out how many of the gentlemen and or ladies we have in our class, but we're only going to use this as a quick example. So there was a total tally here. That means that 6 of those were for the ladies, 4 of those were for the gentlemen. Now if I put that into fraction form, it would be 6 out of 10, because we did 10 total trials, and 4 out of 10. Now to turn the fraction into a decimal, you divide the numerator by the denominator. So in this case, you would say, what is 6 divided by 10? Now we know that 10 doesn't fit into 6, so it creates that decimal for us. I say decimal, decimal. I add a 0 to start that division. 10 goes into 60 6 times. 10 times 6 is 60. Subtract 0. 6 out of 10 is 0.6, or 6/10. That means that 4 out of 10 is going to give me 4/10. So as a decimal, I'd write these like this, 0.6 and 0.4. Now to change that to a percentage, you take that percentage, or that decimal, multiply by 100. When you multiply by 100, in that case, you're actually moving the decimal 2 places to the right. So this is going to be 60% of the sticks that we pulled were for the ladies, 40% of the sticks that we pulled were for the gentlemen. Now, to calculate experimental probability again, you're going to run a type of test or experiment. You're going to keep track of the total number of trials and then the total number of tallies and or frequency for each of the different categories. This is just one example that would help you understand how you actually come up with what would be your probability in a fraction form and how to change that probability from a fraction to a decimal and to a percentage. On page 54, let's take a look at how experimental probability is used in the real world. Experimental probability is widely used in sports. In baseball, a player's batting average is the probability of a player getting a hit based on his previous at-bats. It is typically expressed as a decimal to the thousandths place. For instance, if a player has made 3 hits after coming to bat 10 times, his batting average is 300. It's read as that thousandths place value, so .300 in baseball terms is read as 300, even though you'd probably say .300 mathematically. Mr. Shane played baseball all the way through college, actually played all the way up until this summer, loves the game of baseball, and actually to find out that someone gets 3 hits out of every 10 at-bats and they bat 300 would be the determination of somebody who's actually a really, really good baseball player. Baseball is a game of failure, and you're failing 7 out of 10 times in this case, but you're successful those 3 times. That means you're actually really, really good at the sport and at the actual kind of artistry that is batting and hitting. Now, in other sports, they're going to keep track of, for quarterbacks, completion percentage. For basketball players, your shooting percentage, which is basically the number of makes versus the number of shots, or the number of passes caught versus the number of passes thrown. It's used all the time. Let's try and calculate this in terms of mathematics in number 7. If a player gets 8 hits in 25 at-bats, what's the probability that he will get a hit on his next at-bat? Express the answer as a decimal number to the thousandths place. So you would take 8, the number of events that occurred, versus 25, the total number of trials, and put that into a fraction. 8 divided by 25. you turn that fraction into a decimal, because that's what it's asking us to do, you would get 0.320. I'm going to add that thousands place 0 and say that this player is hitting 320. It's actually a really good batting average to have if you're having 8 hits out of 25 at-bats. In addition to sports, experimental probability is often used in banking, insurance, weather forecasting, and in business. Here we're going to look at an example in the business world. Quality assurance. It's the way in which a business goes about making sure that the products that they're making are high quality and that they're maximizing the ability to make money off of their manufacturing process. A piston manufacturer is concerned with the likelihood of defects as this affects costs and profits. The manufacturer inspects 250 pistons and finds that 8 of them have defects. It costs money to make something, and it costs more money to have something that has a defect to it because you can't sell these products if they have defects to them. So what does a business do? They try and improve the overall quality of what they're making. Letter A. What's the probability a piston will have a defect? Express the probability as a percent. Well, the defect is what we're looking for as the event, so I would have 8 in my numerator and 250 in my denominator, and I divide 8 by 250. I get 0.032 as my decimal. Now to change that into a percentage, I multiply by 100, move the decimal place over, it's 3.2%. 3.2% of those products that you're making are defective. That means 3.2% of what you're making is actually costing you money, not benefiting you. If the same manufacturer produces 3,000 pistons, how many will likely have defects? Now we use the same percentage and apply it to the larger number. So you take 3.2%, turn it back into a decimal. Move that decimal place over, it's 0.032 and multiply by 3,000. You're going to get 96 pistons. Out of every 3,000 you make, 96 of those have a defect. Those 96 are costing you money. Now, in letter C, let's look at how much that's actually costing a company, why you'd want to care about this in the business world. Pistons sell for $35, and it costs $25 to make, so there's a $10 profit margin. Every one you're making and then selling, you make $10 on. In materials to make each piston, how much profit would the manufacturer likely make on 3,000 pistons if the defective ones cannot be sold? Well, let's look at how much money they make overall. How much would it cost to make all the pistons? You take $25 times 3,000. That's $75,000 to make those materials. How many of those were defective? We calculated that it was 96 that were defective. How many pistons are not defective? Well, how do I figure that out? If I made 3,000 and 96 were defective, if I subtracted that value, I would get 2,904 pistons that are good. How much revenue can be sold if all those good ones are made? So 2,904 times 35 is going to give me $101,640. And now I subtract my $101,640 from what it cost me to make them, $75,000, and I'm going to get my product overall, my profit. If you subtract those two, you get $26,640. That's how much money you're making. Now, what about the 96 that you didn't make? You would take that 96, multiply by $25, and subtract that from your overall profit, because that's what you're actually missing out on if you calculated just your straight profit from the 35 without subtracting. So we did that in two ways. Your still overall profit is $26,640, or you could calculate 3,000 times 35, get your total, and then subtract 25 times 96 from that overall value. You'd still get the same answer of $26,640. Okay? That's a good example of how sales and business work with making sure that your probability and your percentages are going to be correct to maximize your profits. You'd be very valuable to a company if you were able to make sure and monitor quality assurance and improve that quality assurance. In the next section, it gives us two more definitions. A random event is an event whose outcome cannot be predicted. For example, drawing a card labeled 8 from a bin of cards, each labeled with a number from 1 to 100 represents a random event. An experiment could be conducted to determine this experimental probability of drawing a card labeled 8. However, it is not always practical to conduct an experiment to determine an experimental probability. In some instances, it makes sense to perform a simulation. A random event using models such as numbers, cubes, spinners, coins, or random number generators. Oftentimes, simulations are used to speed up what would be the likelihood of an event, or to get some type of scientific or mathematical basis for making a decision on what you want to do, rather than having the ability to test that over a long period of time. So the way in which a simulation works in terms of probability in mathematics and science is that you're going to be able to come up with some type of reasoning based on the quick experiment versus a long tapered out experiment that would take more time. We're going to jump to our investigation practice on page 55. Your assignment for Investigation 1 is the investigation practice. We're going to go back and now apply the things that we've learned in terms of how to communicate probability as word problems, how to calculate frequency and turn that into what would be a fraction and percentage, and show that we know what experimental probability is by simply looking at a table, or even if we were asked to carry out an experiment ourselves. Top of the page it says to describe each of the following events as impossible, unlikely, as likely as not, likely, or certain. Now you can refer back to what was page 53 for the chart at the top of the page that shows you what those words mean in terms of their percentage. Let's take a look at A, B, C, and D. A, Gavin rolls an even number on a number cube. You would think of the number of numbers on a number cube and then how many of those are even to create your denominator as the total number, and then the numerator would be the number that are even. Letter B, in the northern hemisphere, the temperature will get above 90 degrees Fahrenheit in the month of July. Think about what summer is like here, how many times it gets above 90 degrees in July, and come up with an estimation of that percentage. Where does that fall from 0 to 100% likelihood? C, the first person that Sonia meets is a left-handed person. How many people do you know are left-handed, or is right-handed more dominant? That might skew your understanding to say, well, this is actually less likely and be on that side of the percentage scale. D, a player with a batting average of 875 gets a hit on his next at bat. 875 is one of the best batting averages Mr. Shane has ever seen. That would probably give you the likelihood of saying the next time, wow, this person's really good before, he's probably going to be still pretty good when he comes up next. In the next section, we have a spinner being spun. Jamie spun a game spinner and recorded the results in the table. The spinner has 3 sections to it, and the spinner lands on A, B, or C in those sections. Here's the frequency of those things being calculated. So it's been spun a total of, if you add these up, 10 plus 6 is 16, plus 9 is 25 times. Now, on your homework page, I've actually written in the next category over here as the fraction, the total number of 9 out of 25, 6 out of 25, and 10 out of 25 to show your experimental probability. And then in this question it says, what is the probability of landing on A and B and on C? Express each as a fraction and a percent. I've already done the fraction portion for you. What I'd like you to do is turn that fraction into a percentage by dividing the fraction, the numerator by denominator. So this would be 9 divided by 25. It's going to give you a decimal. Take that decimal, multiply by 100 to get a percent. Same thing here. 6 divided by 25 is going to give you a decimal. Take that decimal and multiply by 100 to turn it into a percentage. You can write those answers right down below here. It might even work best if you write them below A, B, and or C. Letter F, which letter will Jamie most likely spin? Now you're going to make that decision, the prediction, based on the previous trials or experiment that you've taken a look at. Here's where we're applying experimental probability. We've got these probabilities of things that are going to happen or maybe going to happen, and you make your guess, your estimate, based on, or prediction, based on which one is going to have the highest percentage or highest likelihood of happening. And finally, letter G. If a baseball player has 18 hits and 50 at-bats, what is the probability that he will get a hit in his next at-bat? Express your answer as a decimal number in the thousandths place. And this goes back to the example problem that we took a look at on page 54. Number 7, you would take 18 as your numerator, number of hits, and 50 as your denominator as the total number of attempts, and you would divide those two, 18 divided by 50, to come up with your decimal number in the thousandths place. That's going to give you the batting average of that player. We're at the end of Investigation 1, and I want to reward you for watching all the way to this point in the video. Today you've learned about probability, experimental probability, random events, and simulations. You walked through the different examples on how we turn that probability into a word form to be described, and also how to describe that in fraction, percent, and decimal through the problems we did together. Just give you your assignment in which you'd follow through and do those things in your investigation practice. Because you've watched all the way to this point, I want you to write homework pass in big letters all the way across the front of your investigation practice. If you've watched to this point, you know that that's what you're supposed to do. Thanks for watching.